You're looking at the closest images of the Sun ever captured. On Christmas Eve 2024, in early 2025, scientists analyzing the latest data sets from NASA's Parker Solar Probe announced a discovery that is reshaping our understanding of the Sun. During its 2024 and early 2025 close passes when Parker skimmed just 3.8 million miles from the solar surface, the probe detected a previously unknown solar phenomenon now called the flux veil. NASA's Parker Solar Probe made history. It became the fastest object ever built by humans, zipping through space at a jaw-dropping 430,000 miles per hour or 700,000 kilometers per hour. Even more impressively, it flew just 3.88 milliami from the Sun's surface, a distance so small that if Earth and the Sun were a foot apart, Parker would have gotten within a half-inch of the star. And now we'll finally get to see what Parker saw. For the first time, we have direct images of the solar wind and core anomalous ejections captured from right where they begin, the outer atmosphere of the Sun. The solar wind is a continuous stream of charged particles, mostly electrons and protons, that flows out from the Sun's corona. As these particles race through space, they carry the Sun's magnetic field with them, shaping a giant magnetic bubble called the heliosphere. This bubble acts like an invisible shield, protecting all the planets in our solar system from harmful cosmic radiation. These incredible visuals were captured by an instrument aboard the spacecraft called WISPR, short for Wide Field Imager for Solar Probe. WISPR doesn't look directly at the Sun. Instead, it captures visible light from solar material as it bursts away from the Sun. When these images were taken, Parker was flying within the Sun's atmosphere. It was literally touching the Sun. You may have heard that phrase before. Parker touched the Sun. But how can a spacecraft touch the Sun if it's still millions of kilometers away from what we see as the surface? The answer lies in understanding what the Sun really is. Unlike Earth, the Sun doesn't have a solid surface. It's a gigantic ball of ionized gas or plasma. What we usually see as the Sun's surface is actually the photosphere, the region where the gas becomes dense enough to emit visible light. But this isn't a solid layer. It's more like a fuzzy boundary in a sea of plasma. The Sun's atmosphere gradually thins out above the photosphere. There's no clear dividing line, just layers of increasing Gleitrander lower density plasma. So when Parker entered this outer atmosphere, the corona, it was in a very real sense flying through the Sun's material. The WISPR images give scientists a closer look at what happens to the solar wind shortly after it is released from corona, the outermost layer of the solar atmosphere. If you look closely at new images, you'll notice something remarkable. A dramatic collision of three massive solar eruptions known as coronal mass ejections or CMEs. These are powerful blasts of solar plasma and magnetic field hurled into space from the Sun's outer atmosphere. But what's truly fascinating is what happens when multiple CMEs erupt one after another. These aren't isolated events. Sometimes they collide and interact in space, creating far more powerful effects than a single CME. Understanding how these solar eruptions behave and merge is crucial, especially because it directly affects us here on Earth. When these powerful solar storms reach our planet, they can light up the skies with brilliant auroras, even in places that don't usually see them. But they can also cause serious problems, damaging satellites, disrupting power grids, and exposing astronauts to high levels of radiation. We've already seen the consequence firsthand. Remember the massive solar storms of May 2024? Those were triggered by a series of eruptions from a highly active sunspot region. But what made the storm unusually intense was that three CMEs collided mid-journey, merging into what's known as a cannibal CME. This powerful combined wave slammed into Earth's magnetic field, producing spectacular auroras across the globe, including regions that had never witnessed them before. This is why Parker's close-up view is so important. By capturing these solar events at their source, we can start to understand, and perhaps one day predict how space weather might impact life on Earth. If you look toward the far left of the images, you'll spot another fascinating feature, a region that marks the heliospheric current sheet. This may sound complex, but think of it as a vast invisible structure that plays a crucial role in shaping space weather. To visualize it, imagine looking at the Sun from the side. The current sheet would appear like a giant twirling ballerina skirt, spiraling outward into the solar system. It stretches far beyond the planets and wraps around the entire Sun. But what exactly is it? The heliospheric current sheet is a boundary where the Sun's magnetic field changes direction, from pointing north to pointing south. It forms as the rotating Sun spins its magnetic field out into space. And this constantly moving sheet remains a permanent feature of the solar wind. Why does it matter? Because the current sheet can influence how solar eruptions like CMEs travel through space and how strongly they affect Earth, its own of the key regions scientists need to understand in order to better predict effects of solar activity. Back in 2018, NASA's Parker Solar Probe made a surprising discovery. It detected strange sudden zigzags in the flow of solar wind. These rapid changes, known as switchbacks, looked like the solar wind was folding back on itself in quick bursts, almost like magnetic whiplash. These weren't just isolated blips. Even in Parker's earlier flybys, switchbacks were seen clustering together, hinting that they weren't random. But during the most recent close encounter, scientists noticed something new. The switchbacks were more frequent, more intense, and even better defined. But these aren't just strange solar hiccups. They might hold the key to solving one of the greatest mysteries in solar physics. Why is the sun's outer atmosphere, the corona, hotter than its surface? It seems counterintuitive. The corona, which stretches millions of kilometers away from the sun's core, reaches temperatures over 1,000,000 C. That's 200 to 300 times hotter than the photosphere. If switchbacks are indeed caused by energetic magnetic events like our connection, they could be carrying energy from the sun's surface outward, helping to heat the corona to these extreme temperatures. By studying these zigzagging flows up close, Parker might finally help crack this decades-old mystery. The Parker Solar Probe is far from done. In fact, its most exciting phase hastily just begun. Between now and the mission's planned end in mid-2026, Parker will complete several more close passes around the sun, each one deeper and faster than the last. After its final Venus gravity assist in 2024, the spacecraft is locked into a record-setting orbit that brings it within 1/10 the distance between Mercury and the Sun. With each future orbit, Parker will fly through more intense regions of the solar corona, enduring higher temperatures and radiation levels than any spacecraft before. Its carbon composite heat shield, already tested in the December 2024 encounter, will continue to protect its instruments from external temperatures that can exceed 1,400 C or 2,600 F. Parker's data will be combined with measurements from European Space, a solar orbiter, which orbits further out, but carries powerful imaging instruments. Together they provide a 3D picture of solar phenomena. Parker measures from within while Solar Orbiter watches from afar. Like Voyager revealed the edge of the solar system, Parker is revealing its origin. It's a once-in-a-generation mission that is rewriting our textbooks. One question we get asked all time is, how does the Parker Solar Probe not melt when it dives into the sun's atmosphere? It's a fair question, and the answer lies in some brilliant engineering. We recently published a video that breaks down exactly how Parker survives this hellish environment. If you haven't watched the video yet, be sure to check it out. It's one of the most fascinating aspects of the mission, and it might just change the way you look at space exploration. With Parker's final orbit scheduled through 2026, scientists expect even more detailed measurements. The final plunge may allow Parker to map the flux veil in unprecedented detail, possibly solving the solar wind mystery once and for all. ****